Hello everyone, it's December 23rd. Well, and we're doing for today, so which means I didn't do it last night. I forgot. Alright, but it doesn't matter. I'm gonna do it today anyway. So the first one is course schedule. Alright, when did I do it last time? Oh my, last time was 2020. Oh, it's a hard one. I didn't get it. I didn't get it after 1 hour. Okay, I'll probably change this. Alright, let's see. There are a total of num courses you have to take. Label from 0 to this. You are given an array. Prerequisites. Oh, shoot. I forgot to do one thing. Hold on. I forgot to pull down. Uh, the REPL. Because currently I am here. This is my new laptop. Not new laptop. My other laptop, my MacBook Air. So I need to pull it down. Hold on. So we're gonna just clone it. Okay. I forgot to clone it. There you go. Alrighty. Alright, so let's keep going. You're given an array of prerequisites. I kind of remember. Prerequisites I equals AI BI indicate you must take BI first if you want to take course AI. For example, pair 01 indicates that you take class 0, you have to first take class 1. Return the ordering of courses you should take to finish all courses. If there are many valid answers to any of one, if it is impossible, return an empty array. Okay, so courses 2 represents this, so we need to take 0 and take 1, so I have to take 0, 1, right? So in this case, I take 0, right, and then I can take 2, then I take 2, then I can take 1, so 2, 1 is fine, but both needs to get 3, okay? Example 3 is nothing. Okay, so we have 2,000 courses. Prerequisite start length smaller or equal to this time this, that's for sure. And it's 2, and then they're not equal. All pairs are distinct. Okay, so this is pretty obvious. I think it's a graph. So we're gonna just try go with a graph. All right, so how do we go with a graph? Let's use this as an example, right? So we have courses 0. So 1, 0 means 0 goes to 1, and it's a directed graph, right? It's not it's not an indirect. What's that called? It's a directed graph and non-directed. It's a directed graph. 0 to 1, right? And 0 to 2. Okay, that's fine. And 1 to 3, and 2 to 3. Right, so that's the graph. So the goal is to traverse this graph. Right, the goal is to traverse this graph to see if we can get all the classes. Okay, so that's actually not true because with 3, it requires 2 classes, right? It requires 1 and 2. Wait, hold on. Yeah, so 3 must be taken after 1 and 2 are taken, right? So that's not a simple graph. Because it's a graph, I go 0 to 1, right? And I can go 1 to 3. But in this case, 1 to 3 I cannot go. So I have to wait for 2 to 3. Let's see. I must take this in order to... So maybe we should do it the other way. Yeah, the ideal is we must take these classes in order to take this. So what? Once we build a graph, right? So every node All right, so we need to see which one has no requirements, right? That yes, the one that without requirements will be the starting point. So we're gonna go through, we build a graph, right? So we build a graph, and 0 will basically to 1 and 2, 2 will basically to 3, and 1 will to 3, and 3 is nothing, right? So based on this, so we have two things. So this is the next. So we also need to know what do they need, right? 0 needs nothing, 1 needs 0, 2 needs 0, and 3 needs 1 and 2. So that's a different graph, right? That's a different graph. So I can use this, right, to find out where we're going to start. So for example 2, we're going to start with 0 because 0 doesn't have any requirement, okay? So we go to 0, then we traverse. How do we traverse? Well, we can traverse. Now we try to traverse maybe BFS instead of DFS. What would DFS do? So DFS do would just 0 over to the next one, go to 1, right? And from 1, we look at 1 has only one requirement, so 1 is fulfilled, right? And then from 1, we go to the next one. Okay, so the next one is 3, so we go to 3, and now I check 3 requires 2 classes, right? And then I only have 1, so I can remove one of the class, but we can now go. So we return back to 1, and then 1 nowhere to go, return back to 0, right? And from 0, now I go to 2 done, and I go to 3, and 3 can. So it seems to me that it's a graph, right? And then we can use DFS. It's always easier to do DFS. And every time we hit a node, we need to evaluate whether that node can be visited or not. And that depends on a second dictionary, which we will list each node's requirements. It's going to be a set, right? And then whenever a node is encountered, we also need to know who leads to it, right? So the parent, so we need to have parent as well. So who leads to it? Which is fine. I'll use parent. Yes, it's fine. It's just parent, and then basically means who leads to it, and then we remove that value from the set. And then once all the value is removed, that node is visited, right? Yeah. Let's give it a shot. All right, you want to give it a shot? Okay. Okay, I need to. Doesn't matter. Let's just do the 22. Oh boy, probably this. Man, I gotta list it. I don't know. Oh shoot! I think I forgot to. I know why. I forgot to sync this with my other laptop, which is fine. So, which is fine. Let's just do 20, right? We copy to this 1223, 2021. Okay. Hey, look at that. They changed it. Huh. Okay, it's not too slow. It's actually faster than my other laptop. But this is too small, so we need to make it bigger. And then we need a ruler too. Oh, that's something I forgot to do. Hold on, let me go to settings. Ruler. Yes, we need a ruler. Let's set ruler to how much? 79. How about that? 79. Okay, now we have ruler. Next one, we should make this bigger. Okay, that's big enough. All right. All right. So, all right. So what we're gonna do first. We're going to do adjacency list, right? And we can call it graph. So graph is going to be a dictionary, but we can actually say it. Let's make it even bigger. Yeah, it's not just a dictionary. Let's go default dict. So from collections import default dict. All right. So graph will equal to default dict of list, right? And the other is, what is the other one? The other one is, let's call it prereqs. How about that? Prereqs equals default dict a set, right? And now we say for course, right? For course and prereq in prerequisites, right? Then we say graph prereq dot append course and graph course, not graph course, prereqs course dot add prereq. So all right, so we get this done, and then I'm going to say def dfs. So what we need is the current, the parent. Current will be an integer. The parent will be an integer. Current parent. What else? Do we visit? Yeah, we have to visit again unless it's, well, if a class has been visited, then its set will be empty, right? And if set is not empty, do we still visit that again? If it's, well, actually, the class will only be visited if everyone has merged onto it, right? That's the only possibility. Okay, and we only go from this class when we have figured out. Okay. So there will not be duplication of visiting. There will not be. So I think this should be sufficient. So we're gonna return this one, return none, and the rest will equal to this. So this is the order, right? And where do we start? We handle this one later. So we have a parent, we have a current, right? So if parent is larger or equal to 0, right? If it's smaller than 0, then we don't have to do this step. So if it's larger or equal to 0, then we're gonna say prereq, right? Prereqs current that remove parent, right? And after removing parent, now we're going to check. We're going to check to see if this class, then we're going to see if len prereqs current is equal to 0. That means we have done all of its prereqs. Then we say rest.append current, right? And else, right? If it's this, else if it's not equal to 0, then we return or cannot. Moving on. So we can simplify this as if this is larger or equal to 0, then we do this, and we say if this, I can just say if it's not equal to 0, then we return, right? And then we add this. Now then we're gonna, from current moving forward, we're gonna say for next in graph current, right? DFS next parent is current. So we'll go finish everything, and then return, right? That's that. And how do we start? So we need to go through, right? Go through the, oh, wait, I need another one. Let's call it roots. It's gonna be this. So the course actually not here. So roots will equal to for course, right? In prereqs, if len, actually the items, right? So for course and for C and P in this, if len P is equal to 0 to start with, then we record C. So that's my roots, which, yes, we have to do it this way because we're changing, so we cannot do it later. So now I have roots, then just say for R in roots, right? We'll call it DFS R and parent minus 1, right? Because initially we don't have a parent, that's why we have to check. And once we're done, we're gonna return the rest. Okay. All right, let's try this one. See how it goes. So we have example 2 and 1 0. Right. So it's 2 and 1 0. This one return value is 0 1. All right, and then we have, oh, I didn't even use number of courses. Huh. Well. I think we have an issue here. So, which means, I think that's not the best way to do it. Yep. So I think this will be easier. So C, this, right? For C in range, num courses, and then this one will be C set C in range num courses, right? And then we do blah 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 blah. Then we have this. Yeah. So this one will have full courses. Yeah, because it's possible. Like there are courses that doesn't have prerequisites. Okay. And courses 1 like this, it doesn't have prerequisites, and then we just return 0. Okay. So now we have num courses prerequisites. What's this? This is going to be find order num courses. Tried it. Well, it didn't look nice. Oh, my bad. I forgot to add prerequisites. What is this? It's not iterable. Huh? Hold on. Dot items. Oh, parentheses. Alright. So we fail. So 0, 1, 2, 3. 0, 1, 2, 3 is also an answer. So one correct course, another. So we just need to return one of them. So this one's correct. Okay. If I do it there, let's just go for it. If it's wrong, then it's wrong. Let's see. Nope. I got a wrong answer. It's fine. I'd expect it. Alright, so what is the expected answer? Expected answer is empty. Oh, this one doesn't have anything. Okay, let's draw it out. I think it's probably the same as I had in the past. Alright, so we have 0 to 1, and 0 to 1, 2 to 1, right? And 1 to 0. Holy guacamole, what is this? Okay, so 0 to 1. Hold on. So 0 goes to 1. 1 goes to 0. 2 goes to 1. So that is the graph. And the prerequisites 0 prerequisites is 1. 1 prerequisites is 0 and 2. So 1 has 2. And 2 does not have prerequisites. So we're going to start with 2. Oh, that's why my answer is 2, right? Hold up. So this one basically says we'll start with 2, right? And then what happened? So I start with 2, and then prerequisite is 0, we add it, right? And for next, so 2, the next is 1, okay? So we'll go to 1. Now we are at 1. Prerequisite is 2. And we're going to remove 2. So 1 has 0. Then we just get out. Oh, we should not. Okay, we should do this. We should return res. So we need to check, right? Because if every class is taken, then in the prerequisites, all of them shall be empty, right? So I'm going to say if all something else this. All what? I'm going to say p. I'm going to say len p shall equal to 0. So every class shall equal to 0 for p in prereqs dot values. Okay, this one is fine. Okay, so I don't think we change anything. So basically what we change is the condition at the end. We add one more condition before we submit. Try this. Yep, this one is right. So we got this. It's good, right? 104, 96. Yeah, this is good. So yeah, I think we did better than last time. And it actually is faster. I feel it's faster at 210. So we create two adjacency list. One is for the graph, where prereq goes to the next class, of course. The other records how many, right? It's a set of prereqs to take a certain course, right? And then we DFS on the graph, but the condition for continuing the DFS is when our courses prereqs have all been fulfilled. I just realized that it's possible we don't use this because it's only 2000, right? So it's possible for this just to be I don't know. No, actually set is easier. Have all been fulfilled. And after the DFS finishes, one last trick is to check whether any course has not been taken. The sign that a course has not been taken is that it still has prereqs not removed. And I believe it's actually not ON. Some node can be visited multiple times. What do they call it? ON squared? I mean, the worst case scenario, right, will be everybody connects to everybody else. So each node will visit. Yeah, so I think the worst case scenario is for worst case, right? Worst case scenario. And this one runs in 104. Not 1000, 104. This is 44% ranking. Okay. Let's just check the previous solution. Kind of actually good enough for us to. Okay. And look at this. So graph, oh, in and out. Okay, that's actually a good way. In. That's true. Oh yeah, we can save time by just the number of in nodes, the number of out nodes. Out nodes, yes, will require a child because we need to know which one will go. But in nodes, it doesn't matter. It doesn't matter, right? And that's the BFS, right? That's BFS order dot append, and if a child in dot out minus, if not, no more requests. Oh yes, yes. The let's write it. Yeah, this is better. I like this one better. So let's do solution 2. Right. So let's just say this is a better version of graph traversal using BFS. Reference is my previous solution back in July 2020. All right, so how do we do this? Yeah, I want to follow the same thing. So we have a graph, and with graph we have an in node, which is a 0, right, and an out node, which is a list. So use one graph, one dict to handle both in and out edges. I'm pretty sure this one, I'll do this, edges, right? Then we're the same for this. Right, for this, I'm going to say graph in node, right? Course. Oh, that is not right. It shall be. Hold up. It shall be every. Hold on. In node. It shall be a dictionary, right? Out node. It's also a dictionary. That's actually a default dict. There's a default dict of list. This is going to be a default dict of integer. So graph in node. Who's in node? Course require prerequisite, right? So it's the course, and then plus equal 1, and graph out. Who's out? Prerequisite out dot append course. So we're done, and we say q will equal to this. So it can be 4. For course, which doesn't have in node, right? So for course and num in graph in, right? Dot items. If num in is equal to 0, and now we record this. So that's the q, and DFS while q temp is this, and then for c in q, all right, class in q, result equals this, rest dot append c, right, and then we're gonna check, all right, we're gonna check what? We're gonna check to see graph. Now the in node. Hold on. So C is the class coming out, right? So the class coming out. Hold on. The class can only be appended. Say if graph in node of this class is equal to 0, then we append it, right? Otherwise, we don't. Okay? And then what? I have bunch. And then we can go to the prerequisite. So if it's 0, we're going to append it. And what if it's not 0? So we visit a node who is not 0. Then we just discard it. We don't have to worry about it, right? That means it's not ready. We're going to hit it via some other means, okay? All right, so we'll restart append, right? And then we have its children, which is the out node. And then we're going to push each children, right, into the queue. Right, should we push it into the queue? Queue shall be the nodes that can be visited. Okay, if queue contains only nodes that can be visited, so we have to do a little bit check before pushing into the queue. So we need to check if this equals 0, then we push into the queue. Okay, so for any course, how do we know? A course has an in node, right? And then if I visit a node, so C is the one that's visited. So whoever has C, wait, hold on, how do we do this? So C can be appended, right? And then C has a bunch of out nodes, which is a class they can lead to. And each of those out nodes need to be minus equal to 1. Yes, that's so. Hold on. So this one will be here, right? And then for child, for next, I don't say next in graph out C, right? Then for every one of them, graph in next minus equal 1. And if any one is 0, then we push that into the queue. If it's not 0, then we don't do it yet, right? And I'm going to say if graph in next equal to 0, right? If it equal to 0, then we say temp dot append next, and then blah 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 blah. So we're done. Q equals temp. All right, now it's coming out. Return res if something. You can say if sum equals 0, else this. Sum what? All the in nodes have to be 0. So graph in, right? We say v for v in this one dot values. All right, let's see solution 2. It'll work. So I forgot this. Okay. That's not good. Okay. A serious issue for this one. Graph 1 and 1. Huh. But rest, we have rest, right? Oh, rest is also nothing. Out nodes 0 to 1. In nodes. Wait. Oh. Oh, I see. Oh, I see. It has to be this. Damn it. So, oh, C0 for C in range. Num courses. Yeah. Yeah, now it makes sense. How did I not realize this? Alright, that's fine. This can be this for C in range num courses. There we go. This one pass. There we go. Nice. So this is the other solution, which I think will run faster. So we don't have to handle the set. Yeah, it is faster. So this one is faster because we do not have to handle set. And it's running at 88 milliseconds and 98. Ooh, ranking. Alright, just glimpse through the solution, see what it is about. DFS. I think it's the same idea. Color. I remember to have color. Well, I don't know why they need to use color. Oh, they use this to indicate whether a node is good or node is not good. I remember. Node integrity, now that's the one. That's the one that we have. So instead of dot values, we can just loop through num. Oh, that's actually a better idea. Hold on, I think that's actually a better idea. Which means in node is default dict int. Yeah, I like this. Out node is default dict list. So I still like this setup, but of course this one will give us wrong because I'm looping through this. So don't loop through this, right? We say sum graph in C, right? C in range num courses. Oh, it's still not right? Huh. How? Oh, and here as well. Oh my god. So this one shall be the same for C in range num courses. If graph in C. Alright, we just say if not. Alright, if not. There we go. That I like better. But it's fine. Let's just call it for this one. Wow, spent 6 hours. Well, just more practice. Just more practice. There's no other way. There's no other way. Alright, so I'll move on to the next one. Integer replacement. Now, I've not done this before. Given a positive integer n, you can apply one of the following operations. If n is even, replace with this. Is that integer? Yes. And is odd, replaced with either this or this. Return the minimum number of operations needed for n to become what? Wait, I've not done this before? This feels very, very familiar. Alright, so we want the minimum number of operations needed for n to be 1. We want n to be even, so we can do this, right? Well, first thought, definitely dynamic programming. right? Which means if I give it a value, like say give them 4, give them 1. 1 is 0. How about 2? Oh, 2, we need to go from 2 to 1, right? And that's one step because 2 we can divide by 2. And how about 3? Okay, so if 3, so for each value, right, there are 2 options. Well, actually, my God, there are 3 options. We can divide by 2, we can plus 1, or we can minus 1. I mean, we can say if it's can we say that if it's an even value, it is always better to divide by 2? I think we can, right? Because if it's an even number, let's say we don't divide by 2, then the only other way is no. It's if it's an even number, we can only divide by 2. It's no question about it. If it's odd of plus 1 minus 1, okay, that's not a question. So this is not odd. 3 is an odd value, so we can either plus 1 or we can minus 1. Do we always want to plus 1? Yes, because if plus 1 give us more gains, then yes. But actually plus 1 and minus 1, they can both give us gains. Because plus 1 minus 1 give us even number, right? But the problem is we're at 3. We can minus 1. Right, at 3 we have 2 ways. Right? We even minus 1. So we can minus 1, right? Now to do minus 1, then basically we just add 2, the number to do 2. Now 2 is 1 step, so we do minus 1 is 1 plus 1 is 2 steps. We can always plus 1. If plus 1 is 4, but we haven't done 4 yet. But what we know is for 4, we will definitely do divide by 2. So 4 divided by 2 basically is 3 plus 1 divided by 2, right? That is 2, but that will require plus 1 and divide by 2 steps. That's 2 steps plus 2, that's 1 step, right? That gives 3. So 3 is 2. 4 by itself. Now 4 by itself is definitely divided by 2. Again 2, so 4 is 2 steps. 5, again 5 we can minus 1, so it's 3 steps. If 5 plus 1, that's 6. Right, divided by 2 is 3. That will be 5 steps, so that's definitely bad. 6 will divide by 2, so it's 3. So if it's in an even number, it's easy. We just divide by 2, so we get a value. So 6 is also 3. 7. 7 we can minus 1, so that's 4. Or we can plus 1, that's 8. Right? So plus 1, 8, divided by 2, that's 4. And then that's also 4. So 7, no matter how you do it, is going to be 4. 8 is going to be divided by 2. So 8 is 3. Yeah, so I think that should be fine. I was trying to see if there's any pattern so we can do it mathematically, but that's fine. It doesn't matter. Actually, this one will be LeetCode 397.py. Right? LeetCode 397. Nice. I think it's faster. I'm very excited. Everything's faster. Oh, come on. Okay, so basically what we're gonna say is, do we need, what's the 2 to the 31st minus 1? Yeah, we're gonna just create an array. I mean, the size of the array, yeah, let's just create an array. It's easier. So 0 gonna be, what's 0? It's not gonna be 0. So 0 is 0. 1 is 1, right? And then I'm gonna say for I in range 2 to n, right? Because I handled 1 already. Oh, we can handle 1 too. Wait, hold on. 1 is not 1. 1 is 0. Right, and then blah blah blah, and then eventually return dpn, which actually is dp the last one, but it's fine, doesn't matter. Okay, so arrange this, and we say if I2, right? So that's odd situation. Then dpi, dp.append, append what? So we're gonna append the minimum value, right? So we want to find the minimum value of what? Of either 1 plus dp I minus 1, right? Or 2 plus dp I plus 1 divided by 2. So I plus 1 divided by 2. Else, now this is an even situation, then dp.append 1 plus dp I divided by 2. And now return this. Okay. So solution, what do we have? So we have, actually we're gonna try this. I'm not 100% sure if everything's correct. All right. So here's what we're gonna do. We're gonna go 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 1,000, 10,000. Okay, run it. Oh, list out of range. Huh, how interesting. Okay, do we got list out of range for this? Interesting. Hold on, this is to 1, right? So I is 2 coming out. I append. Oh, shoot. My bad. My bad. All right, try it again. Yep. So I think this is correct. Yeah, I just need to do this plus 1. Oh no. We're still judging? Huh. Hold on. ON is too slow. Ah, damn. Yo, I thought this one. Oh yeah, of course it's too slow. Okay. No. That is not right. That is not right. Okay. Relax. We'll figure it out. That's correct, but it's too slow. Okay, so for every value, right? I think what we can do, we don't have to do every single one. I think that's the thing. We're given an n, right? We're given an n, and we want to find its if n is, yeah, maybe I go top down will be faster, so we can avoid computing a lot of the stuff. Maybe. All right, let's see. Which one I got wrong? This one. All right. How many do you have? Jeez. All right, we throw a few. That's fine. We throw a few up to 9. and we do this. Let's see, how long does it take? Oh, wow, only 19 out of 47. That's terrible. All right, so it times out. That's fine. So this one, TLE, which means ON is too slow. All right, so let's try top down. So top down, this shall be faster because we do not compute every value. And I hope this one can get to O log n. I think this is O log n. So from functools import cache. All right, so we're gonna cache it. Def helper. What do we need? We just need a num. Right, what do we return? We return an integer. Blah blah blah. And then add LU cache. Max size so equal to none. And then we just return helper n. Okay. So if num 2 is odd, else return 1 plus helper num divided by 2, right? And if num equal to 1, return 0. So 1 is 0. So after this, then we're gonna basically say return minimal of helper becomes 1 plus minimum 1 plus helper num minus 1, right? And 2 plus helper. Actually, for this case, I can just do 1 plus helper num plus 1. Yeah, I'm pretty sure this one still passed. So 1, 0, wait. 2, 2, 1, 3, push in here. See. Yep, there we go. So this is a clear bottom up is too slow, but top down seems to be good enough. Yep, so indeed, top down avoids computation of unnecessary values. And since each step we reduce the value by half, the time complexity is O log n. So it's O log n. And the answer is runtime 32 milliseconds, 68. Yeah, it is DP with all this. Got a discussion. Take a look. BFS. Ooh, that's interesting. Never thought about BFS to do this. Greedy solution. Nope. Maybe you can polish yours. It's all C++. No, most of Volt. Come on. A couple Java solutions. Oh, it used to be an easy question. Bit manipulation. Okay, what is the memory usage? They're complaining about the memory usage. Maybe they got lenient. It is possible. Sometimes they relaxes things, and then the solution that didn't pass in the past can pass now. So I'll just take a look. I don't see this one will use too much because that's O log n, right? Yeah, it's fine. This one's fine. But I'm gonna go through this. I'll probably take a look at another one, and then we're gonna call it top-down approach. Ah. Oh my goodness. Is it proof? Correctness. Nope. I just want to see the bit manipulation. The first step towards solution is to realize that you're allowed to remove the least significant bit. Oh, that is correct. Only if it's a 0, divided by 2, yes. And to reach the target as fast as possible, removing digits is the best way to go. Hence, even numbers are better than odd, which is obvious. But not so obvious what to do with odd numbers, yes. I think you just need to remove as many ones as possible. Nah, that's not true, because if you add it, you could remove faster. Yeah. So I just need to remove as many ones as possible, doing +1 in case of a tie. It's better than. That's the only exception. If n is 3, or n minus 1 has less ones than n plus 1. Ah, it's doing this. Otherwise, increment n. If n is 3, or n minus 1 has less ones than n plus 1, and then decrement. You know what? I don't know. I like the DP one. I like DP solution better. Alright? I think this is easy, it's straightforward. I mean, if I want to, it can even be reduced. These two can be written in one line. Like, seriously. Look. I can call this DP, right? And then this, and we can then say return this. Oops, see daisy. I have return already. So return this if num2 else right else 1 plus dp num divided by 2. Alright, so I can do something like this, which I'm pretty sure it also passes. Yeah, I don't have test cases here, so actually let's write test cases. It'll be fun. It'll be fun. So 3 is 2, 4 is 2, 5 is 3, 6 is 3, 7 is 4, 8 is 3. Alright? Then this is going to be n. This is going to be integer replacement. My bad. Yeah? So again, like I don't see why you cannot just do it this way. I bet somebody must have done it. 3 lines. Yeah, that's about right. Yep. All right, that'll be it. Okay, I'll see you guys tomorrow. Adios.